Thank you very much, and thank you for the opportunity to talk here. Well, this is a conference about asymptotic group theory, and I would like to show some peculiar connection with the type of questions we study, which are maybe also not the completely standard question, but still asymptotic properties and a problem in quantum error-correcting codes. And now this is a very elementary problem. One does not have to know anything about the quantum computation. But let me start with a crash course on coding theory of, say, 10, 15 minutes. And it's, as you will see, this is basically elementary linear algebra for undergraduates, not more than that. And the problem can be expressed, and then I will get to the connection with what we are talking about. So what is a code? Classical code. A code is nothing more than just a subspace of Z2 to the n, of the finite field F2 to the n of dimension k. The rate of the code, the dimension of the code is k, the length of the code is n, the rate is k over n, and the distance of a code, I'm talking about what the so-called linear codes, and the distance of the code is the minimum of the Hamming weight of a non-zero vector alpha in the code. Now, what is the story? I guess everyone knows a little bit about that. You want to send a message of length k, and somehow there might be some mistakes along the way. So instead of sending a vector of length k, you send a vector of length n, and we are talking about a linear transformation from k to n. And we want the distance between the legitimate vectors to be large, and then the receiver will be able to correct. If something will be corrupted along the way, then it can correct it to the neighborhood, to the closest vector. And the distance between two vectors in a linear subspace is itself a vector in the linear space. Therefore, the relevant things is the distance of the vector. And so what we call delta d over n is the normalized distance, and the standard notation in coding theory in such a case is to say that C is a nkd code, length n, dimension k, distance d. Now, what are quantum codes? So I'm going to talk here on the so-called CSS code. This goes after some names. Without giving any background, let me just present the down-to-earth definition. The down-to-earth definition for such a quantum code is similar but different. Here we are talking about two subspaces, W1 and W2 of Z2 to the n. Z2 to the n, we are not talking about complex number. I mean, everything is elementary combinatorial. You have two subspaces, W1 and W2, which are orthogonal to each other. Orthogonal in the standard sense. If you take two vectors, you take the inner product. Of course, this is not the inner product, just the product. There is no positivity here, right? A vector can be orthogonal to itself. But they are orthogonal in this standard alpha beta is sigma ai bi equals 0 in Z2. Now, in this case, the orthogonal complement, well, complement is not really the right word because it's not necessarily complement, but W1 is inside W2 perp, and W2 is inside W1 perp. And the definition of the dimension of a code in this case, the definition of dimension of the code is k, which is the dimension of W1 perp modulo W2, and it's a trivial linear algebra exercise to see that this is equal to the dimension of W2 perp modulo W1, and this is equal to n minus W1, dimension W1 minus W2, right? This is a first year linear algebra, and the definition of a distance of quantum code is the minimum of the Hamming weight of what? Of vectors which are in W1 perp, but not in W2, or in W2 perp, but not in W1. And just like in classical code, we call C NKD code, here the tradition is to do it with double brackets, and this is called a NKD quantum code, if you have such a system. Now, what's the goal?
What is K?
The dimension, K is the dimension of W1 perp over W2. That's the dimension of the code is this quotient this time. Definition. This definition is for classical code and for quantum codes. That C is called a good code if, okay, now this is all this if we talk about one code, but we are not engineers, we are mathematicians. So our n is going to infinity, and when we say code, we always mean an infinite family of codes. And we say that C, if it's a classical or fancy C, if it's quantum, is good code if there exists some epsilons that the delta and R are both greater than epsilon, which means that the dimension and the distance both grow linearly with n. Then this is the classic, then we say this is a good code. Now a very important notion also in the classical code is the notion of LDPC. This stands for low density parity check. We say that the code C, now classically first, classical code LDPC is called LDPC, low density parity check, if C perp is spanned by vector of bounded weight. Let's explain. In the code C, we don't want to have short vectors, right? Vectors with small Hamming weight. In its perp, we do want to have. Why? Because the perp of C are really the linear functional, the linear equations defining C. Now you are getting a very long vector, 10,000 bits. You want to check if it's a legitimate one or not. You want that the checks will be very quick. And that's something which is very important theoretically and practically in coding theory. Similarly, in the quantum world, we say that C is LDPC if both W1 and W2 are spanned by vectors of bounded weight. You really have to remember that Wi is the perp of Wi perp. In some sense, you really want to think of Wi perp as your code, and Wi are the defining equations, and the defining equation should be short. Now, so up to now, some definition. A little bit about the history. The notion of good codes goes back to Shannon. LDPC codes goes back to Gallagher in the 60s. And both Shannon first and then Gallagher proved by random method that a good LDPC codes, a classical code exists. Explicit constructions were given only in the late 90s by Sipser and Spielman using Ramanujan graphs. And this was a big breakthrough, even though it's a fairly elementary work. I presented this in an undergraduate class, the work of Sipser and Spielman. When Spielman got the Navalina Prize a few years ago, then the committee praised this work as one of the 3 good reasons for him to get the prize. Was that it's really changed sort of the it has a real influence on coding theory somehow, these explicit constructions of LDPC code. With respect to quantum error correcting codes, it's good quantum error correcting codes exist, but it's not even known neither by random method nor by explicit method if quantum error correcting good LDPC code exists. And if you really go back to the definitions I gave you, this is a completely elementary problem. You can present it to a first-year undergraduate students. Everything is well defined by linear algebra. Even you don't have to know much linear algebra because, but, and this is an open problem if they exist at all, such codes. What's the connection with the kind of questions usually we are interested in this crowd? And let me show you a connection with some homology and cohomology of manifolds and simplicial complexes. Now let's give a crash course of 4 minutes very quickly about homology and cohomology, because this only over F2, we don't need orientation, so everything is still elementary linear algebra. Let X be a finite simplicial complex of dimension D. For example, we will discuss in a minute, when we'll go to be more fancy, triangulations of manifolds. So what is a simplicial complex? This is just a collection of subsets of the set of vertices, which is closed under inclusion. We'll denote xi to be all the faces, the I-dimensional faces. These are the sets of size I plus 1, so x1 edges, x2 triangles, etc. As usual, we will write I for the I chains, namely the vector space over Z2, everything over Z2 spanned by the simplices, and C upper I for the quotient, the functions. But it will be very convenient in this talk to confuse the two. So don't bother to remember which one is the upper, which one is the lower. Just think either of a chain or of a cochain as a subset of the I simplices, because either you take it as a vector span by now, or you take it as a function, characteristic function of a set. We are really talking about subsets of chain, and these are the, think of them really as the same vector space. That will be the best way for us. Now we have the boundary map and the co-boundary map. As usual, the boundary map just take the boundary of a simplex, the sum of all the codimension 1 subsimplices of it, and the co-boundary is the sum over all the I plus 1 dimensional simplices containing it. And, we all know the standard thing that twice boundary is 0, twice co-boundary is 0. Therefore, the boundaries, the I boundaries are inside the I cycles, and the I co-boundaries are inside the I co-cycle, and the homology group and the cohomology group are just the quotients. But here is another easy corollary of fact 1, which maybe does not get so much attention usually, because usually we do distinguish between cycle and co-cycle, but if you think about them as the same space, you see fact 2, that the perp of the boundaries is exactly the co-bound, the co-cycle, and the perp of the co-boundary is exactly the cycle. This is a 2 lines exercise, which I don't have time to show, but therefore, if you take the, I don't know why I wrote here S, I should really write here C. If you take the boundaries and the co-boundaries as W1 and W2, we are getting automatically, they are orthogonal to each other, because you see, the perp of BI is the ZI, which means that the BI is orthogonal to the BI. So we have here, right, ready for us, we have a quantum error correcting code. So whenever you have a manifold, whenever you have that, you have a quantum error correcting code. Of course, it can be a very bad code if the homology and cohomology are 0. Now let's recall, what is the dimension of a quantum code? The dimension of the quantum code is the quotient, right? Which is exactly the dimension of the homology, which is, we are over a field, and it's equal to the dimension of the cohomology. But if it's 0, then it's not such an interesting code. So the question is, we always have a code. The question is now how to evaluate the parameters of these homological codes. So what are the parameters? The length of the code, we are inside a space of dimension whose dimension is equal to the number of cells, the number of I cells. This is the length of the code. The dimension of the code is the dimension of the cohomology, which is equal to the dimension of the homology. And the distance of the code is something which is maybe not so standard to study, but it's exactly the subject of the so-called systolic geometry. Systolic geometry is usually done, well, usually most of the work done are only in dimension 1. And the systolic is like you take a manifold, for example, and you study what is the length of the shortest closed non-trivial path in the manifold. Or what is the length of the shortest non-trivial representative of in the first homology class. Now, why to do it only in the first? You know, then in recent years, people started to do it also in higher dimensional. Again, Gromov. People means Gromov and following the rest of the world. And then you take and then this is kind of a systolic geometry. What is the area, say, of the shortest non-trivial homology class? Now, if you can do it for homology, why not also for cohomology? If you do it over R, why not to do it over Z2? Well, there have been very few people who have done it so far over Z2, but it's just as natural in some sense. And here is a case where this is exactly, in quantum error correcting codes, that's exactly what is needed. The distance of the code is exactly the length of the shortest representative of a non-trivial homology or cohomology class. Okay, so now we are in business. This is now when we take a family of things like that, then this is kind of an asymptotic problems. So this is the subject of Z2. Moreover, and this is an important remark for this talk, if we take, like some of us like to take, you take one manifold and you take finite sheeted covers of it, and you take a triangulation of that manifold, and you take the covering triangulations, the LDPC, which in coding theory is sometimes the more complicated to get, you get for free. You get for free, because what is an LDPC code? An LDPC code are such code, you remember that W1 and W2 are generated, are spanned by vectors of bounded weight. But now, if W1 and W2 are BI or BI, you know, the boundaries or co-boundaries, then the boundary of, then this is spanned by the boundary of cells. The boundary of cells is of bounded size, right? The size is I plus 2 or something like that. But the same is true for the co-boundary if we are talking about a triangulation which are all coming from this, which are all locally looks the same. If they are all covering some compact manifold, then they are all bounded. So this property you get for free, the LDPC, and then you have to work out the other parameters. And somehow from the kind of an abstract point of view of coding theory, I didn't have time to go to that and to explain why. You see, this is kind of a new challenge in some sense for coding theory, because in coding theory, the history is always that random is the best, and you try to get as close as to random. The problem with these LDPC issues is exactly that random one don't give you this. You cannot get them by random, so somehow other methods should be invented. I don't have time to discuss it, but anyway, this is an advantage of doing the homological code. In fact, if you go backward, you see that some codes which are invented by other methods by various people are really homological, even though they did not define them maybe as homological. So up to now, the good news. The bad news is the conjecture of Zémor. Conjecture or question, like he was pessimistic about that. I learned this subject from a paper of him. He said that if C is homological code, then R times delta square is at most n to the minus 2. Or maybe let's go to the other formulation, K times D square. For some reason, these are the parameters he wanted to check. And he looked at all example in the literatures. He has some motivation from classical coding. And he said that KD square is, for homological code, will be at most n to the 1 plus little o of 1, which is very disappointing, because if we want them to be good code, then K should be constant time n, D should be constant time n, so it should be something like n cube. And he said that, oh, no, they are very nice in quantum. You know, well, I should be honest with you. The current situation with quantum computation is so bad that nobody really takes seriously thinking about n going to infinity, because there's still a problem to calculate 5 times 6. I think somebody managed to do 5 times 3, and this was a big breakthrough.
To factor 15.
To factor 15, I think it's still a... No, that's maybe they managed, no? Or not? It was a big breakthrough. So, but anyway, so they are not worried yet. But I have a friend in electrical engineering who does this for coding. Like, 20 years ago, they were laughing at us mathematicians when we talk about n going to infinity. He told me that these days, in classical code, they work with n equal 200,000. And 200,000 is a good approximation to infinity. Anyway, so good means that KD square should be n cube, and he expected it to be at most 1 plus little o of 1. A student of mine, Eitan Fataya, in fact, proved this conjecture if you start, essentially prove it, I don't want to, if you start with triangulation of manifolds of surfaces of dimension 2, but our main results disprove the conjecture, but don't be too excited, because it disproves it only by very little. But it has some, at least psychological motivation, which I'll tell you. So what I want to present is a kind of a new family of homological quantum codes coming from arithmetic lattices, arithmetic co-compact subgroup of SO41. And I will show that they disprove this conjecture. So let's start with this. So let F be the quadratic form x1 square plus x2 square plus x3 square plus x4 square minus square root 2 of x5 square, and let the group G be all the real matrices preserving in GL5, preserving this quadratic form. And if you take the points, if you take the ring of integers inside Q square root of 2, then it's well known. This is kind of one of the standard examples of arithmetic lattices in SO41 that you get a co-compact lattice, a discrete subgroup, which is co-compact in SO41. Well, the reason for that is basically, I guess this, for this audience, this is well known, but that's the ring of integers is embedded twice in R, and it embedded diagonally in the product as a discrete subring, and therefore GO is a discrete subgroup of SO41 cross SO5, because if we take the Galois twist, taking square root 2 to minus square root 2, then the quadratic form becomes definite, and we're getting SO5, which is a compact group, and therefore the projection is discrete, and by the classical results, Borel, Arishandra, Mostot, Amagava, everyone, someone contributed something to this. We get a co-compact lattice, and therefore we get a compact four-dimensional hyperbolic manifold. Well, if we take the full group, we get probably orbit fold, but we can go to congruent subgroups, which are torsion-free, and then we get finite sheeted covers of it, Mi, which are the four-dimensional hyperbolic problem. Okay, so now let's fix a triangulation of the first one, the full one. If you really care and you don't want to work with orbit fold, doesn't matter, go to one finite index, torsion-free, and fix a triangulation on that. Take finite sheeted cover by the congruent subgroup, important. This arithmetic group has a negative solution to the congruent subgroup property. It has congruence and non-congruence subgroup, but I want to work with the congruent subgroups only. And then each one of them, so if we will denote M of I of the ideal, the manifold of X of I, the triangulation. But it's kind of important to keep the same triangulation and pull it up to the covers. So if we look at this family, we are getting four-dimensional. Now you remember there was another freedom in the choice. We talk about Ci for every I less than the dimension. I want to take I equal 2. And this is crucial. If you do it with I equal 1 or with I equal 3, then Zémor conjecture is correct. It's only for I equal 2 that we will be able to that, and I'll explain later on somehow why. And this is the main results. There exists some constant, which are even explicit if you really want to compute them. We didn't want because it's a lot of work. There exists some constant such that the dimension of H2, you remember H2, the homology, is the same as the cohomology. Here we are over a manifold. Well, here, no, here it doesn't matter, actually. The H2 are the same. And this grows linearly with the volume. The volume grows linear. The number of two cells is linear in the volume. So it means that the rate is fantastic. The rate is best possible. The dimension of the codes here grows linearly with the length. The distance is not so fantastic, but is also not too bad. Every homological, non-trivial, two-cycle or two-cocycle in MI as area at least the volume to some epsilon, which means that it's not linear, but it's n to some epsilon for a fixed epsilon. If you put these together, you see that this is a counterexample to the question of Zémor, because it means that k times d square is at least n to the, what did I do here? N to the 1 plus 2 epsilons, right? Okay, 2 epsilons, also epsilon. So it's n to the 1 plus epsilon, while Zémor predicted that it will be at most n to the 1 plus little o of 1. So this will give us a counterexample. I should say right away that there are known LDPC quantum error correcting codes which are better than these, not good, but better than this one, but non-homological. So in some sense, our work is not important for itself. The only thing which it does is to bring back the homological code into the race. Namely, it brings up that maybe via homological code you can still win, you can still get the good codes. It changed the intuition. I mean, and that's what I want to explain. What was wrong with Zémor intuition and why there is some hope, though I'm not sure, but that maybe homological code can still do better than this one and also than the best known quantum codes. So this, first of all, you understand why the result, why the theorem is doing better than Zémor. Okay, so maybe this remark is the one I really want to explain, because in some sense it's even more important than the technical explanation. The main new insight is that two systole behave two systole, I mean not systole over F2, but systole of dimension 2, namely the homology or cohomology of dimension 2 behave, and 2 and up, behave very differently than dimension 1. The problem is with dimension 1, and if you work with manifold, the problem is also because of Poincaré duality in dimension d minus 1. But let's talk about 1, which is easy to explain. The problem with 1 is this thing which we all know, either for manifold or even for simple graph theory, that if you have a graph and you want to ask what is the girth of the graph, then the girth of the graph is at most logarithmic. And this kills you, because this means that you always have a representative of a non-trivial homology which is very short. So you cannot really be good. And in some sense, this is what was responsible to all the examples that Zémor kind of look at. And this is what responsible why in the work of my student, the conjecture turns out to be correct in dimension 2, because if you work in dimension 2, you only have to play with 1. The point is that when you go up, then you have a chance to have homology. It's certainly not nothing automatic. You have a chance to have homology which is larger, namely, or let's put it in a different way, that there would not be any very short homology classes. And that's exactly what we are showing here in dimension 2. Now, because we are coming from a manifold, it's enough to show it for homology, and then by standard Poincaré duality arguments, it's true also, what is true for homology is true also in the dual picture for cohomology, and we really had to do the work about the distance only once. And not twice. Is it clear? Because that's in some sense the main message. By the way, this is a different work I'm doing these days with Tali Kaufman and Kashdan. which points out it's come from completely different motivation, but there is an interesting systolic inequality. I want to stress that the homology and cohomology do not have to be symmetric if you work with simplicial complexes. In fact, for those of you who know what are Ramanujan complexes, we were proving that if you take Ramanujan complexes of dimension 2, then the minimal representative for homology is logarithmic, and the minimal representative for cohomology is linear. So it's very different than the situation in manifolds. So usually we kind of naively think that, okay, complexes, Bourratit's building divided by gamma is the analog of a symmetric space divided by gamma. This is true in many aspects, but sometimes there are really fundamental differences. And the difference is really the fact that buildings are thick and not thin. Namely, every edge is sitting on many triangles, while if you take a triangle of a surface, then every edge sits on exactly 2. So this is just a side remark, which belong to a different lectures. Okay, so the QECC are still far from being good. That's what I mentioned. In fact, Tillich and Zémor have even better non-homological LDPC, quantum error corrected codes, but this brings to the game. By the way, for these codes that I will discuss, I'll come back in a minute, we know that they are not good. It's not like this is the best we can do. Well, we maybe can improve the constant, but we know that they are not good, and there is an hidden reason for that, which maybe eventually the Zémor conjecture in a weaker form is maybe correct. Maybe eventually it will show that homological, though this I'm not sure. I don't know. Okay, so now let's go to the sketch of sketch the proof. We'll do it very quickly, and we have to finish the talk in a few minutes. So I'll just do a little sketch. Okay, so this is a standard argument which goes back to many people, that if you work with a given arithmetic lattice and you look at a chain of normal congruent subgroups, not normal subgroups by themselves, this is not enough. But if that's the reason we should take congruent subgroup. If you go with congruent subgroup, the injective radius of the manifold grows logarithmically with the volume. Okay, this is a standard argument, and this is the truth. It's really logarithmic. It's not worse or not better. Now, again, you see what happens if you want to look at just on a curve, on a geodesic, because the injective radius is logarithmic, and you take a curve, then a curve will go logarithmic, will come back, right? And then you have representative which are logarithmic. But if you talk about higher dimensional, then the volume of logarithmic in the hyperbolic world grows exponentially in the logarithmic, and we are in a better shape. So now, one more thing, and this is an argument which is an old argument. I don't know, we couldn't find a good reference somehow, but it was proven in special cases in several pieces of work. This is pretty standard argument. Let M, now, here is another fact that we are using. Let M be a two-dimensional hyperbolic manifold of even dimension 2n, and the volume is V. Then there is a formula to the Euler characteristic. The Euler characteristic is equal -1 to the n 2V divided by the volume of the ball. But the most important part for us is -1 to the n. The minus 1 to the n, we are working with n equal 4. With dimension equal 4. 2n equal 4 means n equal 2. And this is crucial because this means that this is a positive number. And basically, that's the only thing we need. That if we start with one manifold of dimension 4, it has a positive Euler characteristic. And therefore, if you go on a chain of finite index subgroups, the Euler characteristics, as we know, what Euler characteristics should do, they grows linearly. Another fact which we had to prove, but it was kind of imitating some old results. As I said, most of the systolic work was done over R, but here I cannot say this is a standard thing to do. Is standard for my co-author Larry Guth. How to move from real to Z2, you have to do a little bit technical work in order to take the classical proof which were done over R and imitate them over. Yet, so let M, so here is the result, let M be an hyperbolic manifold of injective radius at least R, and let beta be a non-trivial I cycle. Then the volume of beta is at least the volume of a ball of radius R in the I-dimensional hyperbolic space. Now, this was proved already 30 years ago by Anderson for characteristic zero homology, and the proof can be carefully adapted also to Z2. Intuitively, it's almost a trivial result. Why? Just think about that. You have injective radius is at least something, right? Is at least R. You have some homology, which is something which kind of closes itself. So you can say it passes through a point, take a ball of radius R around it, and now you have, say you have a surface passing through this point which closes on itself. So somehow you feel that this should really pass through a disk inside that hyperbolic manifold. You cannot get out if you don't get out from all directions. In dimension 1, it's enough to get out by 2 points. But in dimension 2, you have to get out from a full circle, right? At least that's the standard intuition. And this standard intuition one should make into a proof, especially when you work over Z2. But basically, this is the type of argument that you apply here. And if you are expert enough and you know to apply all this machinery, then this can be done. So what does it mean? It means that the non-trivial I cycle is at least as the dimension of the ball. Dimension of the ball of radius R in a two-dimensional ball, right? We are talking about two-dimensional, inside 4, but it's two-dimensional, grows like it's exponential in the radius. The radius is logarithmic, so exponential in the radius is logarithmic in the volume, so exponential in the radius give you the volume to some epsilon. And basically, okay, so the last thing, this, what I wave ends, explained the issue about the distance. Now, what about the dimension? How it follows from the Euler characteristic? This is, again, now a trivial argument, because what is the Euler characteristic? The Euler characteristic is dimension of H at H0 minus dimension of H1 plus H2 minus H3. You see, we are lucky. If we would work with 8, then we cannot do this argument. This argument works exactly to 4 and exactly for I equal 2. Then now H0 and H4 are of dimension 1. So we are getting dimension H2 minus the dimension of H1 twice because of Poincaré duality plus 2. And therefore we get, because we know that the Euler characteristic grows linearly, we are deducing that the dimension of H2 grows also linearly, and this ends the proof, and this ends my talk exactly on time.
Thank you. Are there any questions?
Does the geometric origin of the code allow you to get a more efficient decoding procedure than in general LDPC code? Does the geometric origin of this particular code give you a more efficient decoding procedure than a general quantum LDPC code?
I don't know. We are not really. We are not yet there. You know, you are really raising a very important question. As we should explain this to the non-expert. You know, in coding theory, I single out the two properties, which is LDPC and good codes. But for practical life, you need also efficient encoding and efficient decoding. So after that, you have other parameters. At this point, we never try. I mean, let's be honest. I don't think that this code is going to be implemented. So what's the point here is to show that you can get better code coming from homology and cohomology, and once we'll get codes which we'll be happy with, then hopefully other people will try to decode and encode them.
Any other questions? Well, if not, let's thank Alex Lubotzky again.